Hello mathematicians. We're now going to have a look at something called the trapezoidal rule, which is referred to as a numerical method of integration. And the reason we need numerical methods of integration is simply because even if we know all the algebra, there are some functions for which the exact area by integration is not possible to obtain. So not every function do we have an algebraic rule to be able to integrate. So in some situations, numerical integration, which gives an approximation of the value of the area under the curve, is used. And what most of these rely on, is putting shapes under the curve, shapes whose area we can find, and trying to essentially match the curve to a number of shapes. Now, because we can't always match them exactly, in fact very rarely can we, then they become methods of approximation. But they're reasonably straightforward in concept and to use. So in the trapezoidal method, what we do is to approximate the curve with straight line segments, and those straight line segments mean that the area under the curve can be treated as the sum of the areas of trapezia formed by the straight line segments. So that seems like a lot to get your head around, but here it is with one application. So if we have this curve here, x squared plus 4, which we know we have a method of integrating, so we could find the exact area between 0 and 4. However, if we knew nothing about integrating and we said we want that area under the curve, one way we could do it is draw a straight line from there to there, and we notice that the shape that we form is a trapezium. And we know the formula for the area for trapezium. It's half the sum of the parallel sides, this one and this one, times the perpendicular distance between them, which is this here. So we now dress that up as the trapezoidal rule. So one application of the trapezoidal rule, which is what we've got here, one trapezium, is b minus a, so this is taken as b, this is a, b minus a divided by 2, so that is half the difference between the parallel sides, times the sum of the parallel sides. So the length of these sides, if we've got the function f of x, then the length of the sides are f of a and f of b. So I'll take a moment to convince yourself that that is just saying find the area of this trapezium here. Now, what is all of that doing? Well, it's approximately giving us the value of this integral. And the value of this integral, if we could get it exactly, would give us the area under the curve. So that's what we're doing in concept. We're saying that we're approximating the integral, which in turn is the area under the curve, by finding the area for trapezium, which approximates the shape of the curve. So in this particular example, if we stick the numbers in, we've got 4 minus 0 on 2. Our two sides are 4 and 20, which we can read off the graph in this case. And so that number there, 48 square units, is approximately the value of the integral. It's going to be an overestimate because our curve is concave up. So in other words, because the curve is down like this, when we put the straight line segment in, we must overestimate the area. Now, here's a GeoGebra simulation of the trapezoidal rule. So here you can see that I've broken it into two trapezia. And already you can probably pick up that that area of overestimation is smaller. So with just two strips integrating this curve y equals x squared plus 4, whose exact area is 37.33, then, which is that, of course, then with two strips we're getting a value of 40, whereas with one strip we had 48, so just doubling the number of strips brought it down very significantly. If we bump the number of strips up to 3, the approximation is becoming better. So when we have a lot of strips, So you can see now there's very little difference with 12 strips. If we take it all the way up to 20 strips, then there's hardly any difference. It's within 3/100ths of the correct area. Now, while doing that by hand would be really tedious, this is what computers excel at. So we could set it up to run with 100 strips or 1,000 strips or 10,000. It's not going to make much difference to the computer, and it will get a very good approximation, almost as close as we would like it to get, to the exact area under the curve. So computer programs which do integration, some work algebraically, but most would actually use a numerical method. And the trapezoidal rule is just one relatively straightforward numerical method. So as we've just seen, accuracy is increased by increasing the number of trapezia, so that if we use this rule with 4 applications, so 4 trapezia here, then the width of each trapezium now becomes 1. So it's the trapezium width, b minus a, which is 1 on 2. This is the function of 0, that's 4. The function of 1 is 5. That function of 1 then becomes the left-hand edge of this trapezium, just here. The right-hand edge is 8. That 8 is also the left-hand edge of that one. The right-hand edge is 13, and the 13 is also the left-hand edge of that one. And the 20 only turns up in one trapezium. And we go through, do all of that maths there, and when we do all the maths, we get 38 square units. So, we can, if we don't want to do this, come up with an alternative formulation of the trapezoidal rule. Some people really like this, and in fact for the trapezoidal rule I think it's okay to use this table format, which is that we put in the values of the functions, so that the x values of the functions, the corners of the trapezia if you like. These y values we then just work out, so that's all of these points here, these heights of our sides of the trapezia. And then what we notice is that the strip width is the difference in the x values, so in this case a distance of 1. The inner function values, as we saw above, are used twice, and so the area approximation is the strip width times the function of one end, the function of the other end, and 2 times the function of all the ones in between. So one of these, and 2 of all of those. So let's have a look at this table here. So first step, complete this table. So they're often nice enough to give you a mark for doing that. Occasionally they'll give you the complete table. Sometimes they'll give you a graph. So we plug the numbers in, use the trapezoidal rule with 5 function values. So these are our 5 function values. So they're the x values. These are the f of x's, or the y values, or the heights of the trapezia. And we want to approximate the integral from 1 to 5 of 6 on x dx. Now this is one for which at the moment we have no algebraic method of sorting. We will have later, but for the moment we can't do it with an algebraic method. We have to use the numerical method. So when we write down the trapezoidal rule, it's half of function of one end, function of the other, twice all the ones in the middle, which looks like that in terms of a picture, and that gave us 10.1. Now, the second part said why the approximation will exceed the value, in other words, why it's an overestimate. And when we take the second differential, we see the curve is concave up, which means that our straight line segments will always be above the curve. So on any trapezia, the area of that trapezium will overestimate the area under the curve at that point. We can also use the trapezoidal rule to find the approximate volume of revolution about an axis. And in this case, the procedure for the trapezoidal rule is almost the same, except all the function values are squared and they're multiplied by pi to get the area of that circular slice. So in this question here, if we generated a cone by rotating this line about the x-axis, use the trapezoidal rule with 4 function values and estimate the volume of the cone. So step number 1, I think, is to get a picture so we know what's going on. So there's our line, y equals 2x. Between 0 and 3, we want to use 4 function values, so these are the 4, 0, 1, 2 and 3, and use the trapezoidal rule, but we're going to imagine rotating around the axis. So we're finding the area of the little discs. So half of, so 1 minus, so 1 is the strip width, half the strip width, function of one end squared now, function of the other end squared, 2 times all of these individually squared, multiply it by pi, and we get the area of the cone, 38 pi cubic units. Now you could then actually verify for yourself that that is the volume of a cone, 1/3 the base times the area of the, 1/3 of the area of the base times the height. I'll get it right in a moment. And because this is a straight line, the trapezoidal rule is more than an approximation. It will give us the exact volume. So have a go at these, but before you do that, again, what is the big idea about the trapezoidal rule? What do we use it for? What's the formulation? How do we apply it to finding areas? And how do we apply it to finding volumes? And then go for it.